This video is a guide for getting started with networking in OpenStack or the Neutron project. In it, we will walk through building a small virtual network infrastructure using the OpenStack web UI called Horizon. I'll describe the core Neutron abstractions of networks, subnets, ports, and routers. We will also look at security groups, fixed IPs, floating IPs, and DHCP. The walkthrough in this video is a high-level view. A future video will look under the covers at how these abstractions fit in with technologies like Open vSwitch, network namespaces, Linux routing, and OpenFlow. Here are 3 references for this video. I'll link to these in the video description. The official OpenStack documentation at docs.openstack.org, specifically the networking guide. RDOproject.org. The lab setup I'm using for this video is based on RDO. Finally, Asaf Mueller's excellent blog, which includes many detailed dives into OpenStack networking and related technologies. Asaf is a core member of the Neutron team. Let's start with defining Neutron. Neutron is the networking project for OpenStack. It is responsible for setting up the virtual network infrastructure in an OpenStack-based cloud. Its core components provide basic switching and routing functionality for virtual machines. Neutron also includes more specialized virtual network functions like VPN, firewalls, and load balancing. Through the use of plugins, drivers, and agents, there is inherent flexibility for actual implementations on various hardware and software components. Lab setup. For this demo, I'm using VirtualBox as a hypervisor on my desktop. VirtualBox is open source and pretty easy to get started with. More information can be found at virtualbox.org. In VirtualBox, I'm running CentOS-based VMs to host the cloud. For deploying OpenStack, I'm using RDO. RDO is a relatively easy-to-use option for trying and testing OpenStack. For more information, you can go to rdoproject.org and check out the Getting Started guide. Finally, for this demo, the ML2 core plugin is being used, along with the Open vSwitch mechanism driver and the VXLAN type driver. Now let's jump into OpenStack. Again, the web UI for OpenStack is called Horizon. In Horizon, we are going to create an OpenStack network, subnet, and DHCP service all at once. I'll explain what these abstractions mean immediately after we create them. Note, when creating objects in OpenStack, we are interacting with the OpenStack APIs, like Nova, Keystone, Glance, and Neutron. Working through Horizon is a GUI-based way to interact with those APIs. Horizon. We will log into Horizon using an account named Demo. The user demo is mapped to a project also named Demo. The first thing we are going to do in Horizon is to initiate a virtual network where we can place our VMs. To do this, we will go to Network on the left and select Networks. Then we click Create Network. Let's name this network Net1. We want it to be admin up, and we need a subnet for the VMs, so we leave this box checked. Let's hit Next, and we can see the subnet details page. Let's name the subnet Subnet1. Here under network address, we define an IPv4 subnet in prefix notation. Let's use 192.168.1.0/24. For the network gateway, we can leave that blank. The gateway for the VMs in this subnet by default will be the first usable IP of 192.168.1.1. We hit Next again and leave this box checked to enable DHCP for the new subnet. Now we can hit the Create button. Now let's discuss what we just set up. A virtual network with an associated subnet, as well as a DHCP service for the subnet. Neutron networks. A virtual network in OpenStack is somewhat analogous to a VLAN in traditional networks, but with more flexibility. As many engineers know, a VLAN is a logical slice of the physical network. Systems in one VLAN are logically separated from systems in other VLANs. A VLAN also represents a broadcast domain. Similar to VLANs, an OpenStack network provides a logical space isolated from other OpenStack networks. Like VLANs, an OpenStack network is also a broadcast domain. Separation of virtual networks is known as segmentation. Behind the scenes, various technologies can be used to keep OpenStack networks segmented across the infrastructure. This can include combinations of traditional VLANs, tunneling protocols like VXLAN and GRE, Linux network namespaces, and OpenFlow rules. I do have videos on my YouTube channel talking about some of these areas in more detail. Neutron subnets and DHCP. Once a network is created, a subnet needs to be mapped to the network. The subnet provides a Layer 3 addressing scope for a network. When you create a subnet in Horizon, by default a DHCP service is also launched. This is managed by the Neutron DHCP agent and is typically implemented in Linux with the DNS mask service. Once we've created a network, associated a subnet, and have a DHCP service running, we can launch some virtual machines, also called Nova Compute instances. Let's do that now. Nova Compute instances. In Horizon, under the Compute sidebar item, let's select Instances. Then select Launch Instance. We will keep the default availability zone here. The prefix for the name of our VMs will be blue. The flavor or size will be tiny, meaning minimal CPU, disk, and memory is used for our instances. We will launch 2 VMs at once. The VMs will be based on an image managed by the Glance service. It is a small Linux image just for basic testing. On the Networking tab, there is only one network to choose from, Net1 that we created a moment ago. This is the virtual network where all VMs will launch. Now we can hit launch. Here are the 2 new compute instances, Blue1 and Blue2. The 2 new VMs spin up and receive IP addresses from the DHCP service we enabled. This is the CLI of Blue1. IPA shows its allocated IP of 192.168.1.7. I can quickly check that I can ping Blue2 with ping 192.168.1.8. We can even ping the DHCP service in Net1 at 192.168.1.2. These IPs allocated for our VMs are known as fixed IPs. This is in contrast to floating IPs, which we will cover later. Floating IPs we won't see here on the VM. In the diagram, we see our new VMs linked into the virtual network we named Net1. The OVS agent manages connecting neutron ports for the VMs to the virtual network. Neutron ports. An analogy to neutron ports in the virtual world is rack switch ports on switches in the physical world. Let's see how this looks in Horizon. Here are the network details of Net1. At the bottom is a section for ports. There are 3 ports here. We see each one has a unique ID, an IP address, and a field describing the usage of the port. 2 ports are for the 2 VMs we launched. 1 is for the DHCP service. If we click on a port, we can see that a MAC address is also associated with the neutron port. So this is something different from a traditional network switch port. In Neutron, we have an IP and a MAC mapped directly to the port itself. Building a second virtual network. Quickly now, we will create a second virtual network for this project. This will serve as a fast review. Again, we will use Horizon to do this so that we can see it graphically. First, we need another Neutron network. This one will be called Net2. We will add a single subnet to Net2 named SubNet2. We will assign the subnet the block 192.168.2.0/24. DHCP is enabled again. Let's launch 2 VMs in this network with the name prefix red. Again, we will use the flavor tiny. The instance count will be 2, and we will use the same small Linux image. For networking this time, we select our new network, Net2. They are scheduled by the Nova Scheduler service to compute hosts, assigned IP addresses, and soon are ready to go. We can see the names Red1 and Red2 since we picked red as the name prefix earlier. Here is the CLI of Red1. IPA shows its IP address of 192.168.2.4. We can try pinging Red2 at 192.168.2.3 and we will see if that works. However, if we try to ping over to Blue1 in the other virtual network at 192.168.1.7, we see that times out. Why is this? Back of the diagram, we see there are now 2 networks, Net1 and Net2. However, the 2 networks are logically separated from one another. The VMs have no way to have their traffic routed to one another. To have a routing path, we need to launch a virtual router. Neutron routers. For this demo, we will launch a virtual router. We will attach the virtual router to Net1 and to Net2. Just like with the VMs, neutron ports are created for these links. We see here how the IPs allocated are the first IPs of each respective subnet. The virtual router will serve as the default gateway for the VMs in Net1 and Net2. The virtual router is managed by the Neutron L3 agent. We will see in my next video how network namespaces, IP tables, and policy routing are used in the creation of these virtual routers. Let's launch this virtual router named VR now. Under Network, we select Routers. Then we hit Create Router. Let's name it VR for Virtual Router. For now, we won't select an external network. We will come back to that in a moment. What we will do is add those links to Net1 and Net2. To do that, we select Add Interface. First Net1, now again for Net2. Let's look again at the details for Net1. Looking here at the bottom, we can see Net 1 now has a neutron port allocated to it for the attachment to the router VR. Net 2 will have the same thing. So now we have our two networks connected through a virtual router, and there should be end-to-end routed connectivity between the private networks Net 1 and Net 2. Let's quickly verify this. Here I'm back on Blue 1 at 192.168.1.7. I'll try to ping Red 1 over on the other virtual network. Looks like that works fine. Our virtual router is routing packets between our two virtual networks. What we don't have at this point is any way for our internal VMs to communicate with destinations external to our cloud. In the next section, we will connect our virtual router to an external provider network. External provider networks. A provider network in OpenStack is one which is provisioned in physical network infrastructure. An external provider network provides a path out of our private project networks to external networks and perhaps the public internet. For this demo, I preset up a network called public to represent a provider network. Keep in mind this is a demo I'm running from home, so this isn't a real network. I'm just faking a network with public IP addressing in VirtualBox. To get our VMs in Net 1 and Net 2 external reachability, we will connect our virtual router to this provider network named public. Once we connect VR to network public, a neutron port is allocated and our router is connected to it. The router interface attached to public will get an IP address from the public subnet block of 200.0.0.0/24. Let's do this now in Horizon. First we select routers on the left. Here is our router we named VR. On the right, we can see an option to set gateway. This means to connect to the external provider network. Let's hit that now. We select the network public and hit Set Gateway. Now if we select the name of the virtual router, we get some more detail. One of the items here shows an IP address was allocated and assigned for the external interface of our router, in this case 200.0.0.24. Now we have a path from our private internal project networks to our public external provider network. Our virtual network topology now gives us the ability to rely on SourceNet to provide connectivity from our compute instances to external networks. SourceNet. Use of SourceNet is much like one's network at home with a residential router. At home, you might have a laptop and a desktop both with internal IPs. To get out to the internet, SourceNet is usually used. Your home router would have an externally reachable interface with an IP address used for NAT. When you connect from the laptop to the internet, the packet initially has an internal source IP. When this packet gets to the home router, the source IP is translated to the router's external IP, in this example 80.1.1.1. The same is done for the desktop. Its traffic outbound has its source IP translated to the same single source IP of the router's external interface. Since the same single IP of 80.1.1.1 is used for both, source and destination port numbers are also tracked. Here in OpenStack this works the same way. Perhaps Blue 1 is reaching out to the internet. In the private project network Net 1, the source IP of packets is 192.168.1.7. After a packet is routed by the virtual router, SourceNet kicks in to translate the source IP to 200.0.0.24. This is the external IP of the neutron router. Just like in a home network, SourceNet works fine for outbound traffic from project internal networks to external networks or the internet. However, SourceNet does not work for connections initiated from outside directly to the VMs. For that, we need a floating IP. Floating IPs. Floating IPs are implemented with one-to-one NAT. Again, let's look quickly at the home network example. One-to-one NAT means one externally facing IP address is mapped to one internal private IP address. Outbound traffic from the laptop would have its source IP translated from a private one to a public one. Inbound traffic has its destination IP translated from the public IP to the private IP. The same happens for the desktop, except the desktop has its own unique public IP reserved for it. In OpenStack, the external IPs used for one-to-one NAT are called floating IPs. They are floating because they can be easily added, deleted, and moved between different systems. For example, Blue 1 might have a floating IP of 200.0.0.11 attached to it. We could plan a maintenance on Blue 1 and first move the floating IP to a backup server Blue 2 before doing the maintenance. Let's assign a floating IP to our VM Blue 1 in our demo project. In Horizon, we go to Instances. From the drop-down here for Blue 1, we select Associate Floating IP. We haven't reserved any floating IPs for a project yet. There's typically a shared pool of addresses that multiple projects share. We need to reserve an IP from the pool, so we hit plus here and then allocate IP. Now 200.0.0.25 has been reserved for our project. Here we can associate this IP to our VM. Now we can see the floating IP linked to our VM. With Blue1 having a floating IP associated with it, we have a way to connect to it from the outside. However, there is one thing still blocking us from doing so. Security groups. Security groups in OpenStack provide access control to VMs. In traditional network engineering, this is a lot like access control lists, or ACLs. In Neutron, the security groups are applied at the Neutron port in front of our VMs. This means every VM can have different access rules, even if they are on the same network. Let's look at our security groups now. In Horizon, we go to Compute, Access, and Security. On the Security Groups tab, here is the default group. All the VMs we launched are using the same security group with this name default. I'll select Manage Rules for the default group to see what is in there. Looking here, we can see that all outbound or egress traffic is allowed from these VMs. Inbound is different. IPv4 and IPv6 traffic is allowed, but only if it is from other hosts that use this same security group named default. This means traffic between all our VMs in our project is allowed, since they are all part of the same default group. However, flows from outside our cloud are not allowed. Let's allow SSH traffic from 200.0.0.1/32. This is the IP of my desktop in this demo. To do this, we select Add Rule. We can pick Custom TCP Rule. The direction to allow is into the VM, so ingress here. We want to permit SSH or port 22. So we're permitting 200.0.0.1/32. We can click Add Now, and now the rule is displayed. Let's verify this worked by SSHing to Blue1. From my desktop, I'll SSH to Blue1's floating IP at 200.0.0.25. Username and password go here, and we are in. IPA shows Blue1's fixed IP of 192.168.1.7. We can see how Blue1 has no awareness of its floating IP of 200.0.0.25. A completed virtual topology. Now we have a completed virtual network topology. Let's do a fast review of everything that's been covered so far. That should help solidify all the concepts covered in this video. Quickly before that final review, please bear with me for a quick plug for this channel. If you found this video helpful in any way, please let me know in the video comments, and also please subscribe if you'd like to see when new videos come out. The next video I put out will be a deeper dive into a Neutron setup using DVR, or distributed virtual routing. In that video, I'll show multiple packet walkthroughs between VMs and out to external networks. It will show how Open vSwitch, OpenFlow, network namespaces, policy routing, and IP tables are used together to form the virtual infrastructure we built here. Also, as always, you can connect with me on LinkedIn at www.linkedin.com/in/David Mahler. I'd love to hear back from folks watching these videos. Final review. In this video, we set up a virtual network topology through Horizon. We started by creating a Neutron network, which is a virtual network segmented or isolated off from other networks. Neutron networks can have one or more subnets associated with them. Subnets are where Layer 3 addressing is carved out. Subnets typically require a DHCP service, and this is enabled by default in Horizon. Also by default, subnets reserve the first usable IP to be used as the default gateway. When Nova compute instances or virtual machines are launched in a network, Neutron ports are created, and an L2 agent like the OVS agent connects VMs to the virtual networks. Neutron ports have IP and MAC addresses associated directly with them. Neutron ports for VMs typically have security groups also associated with them. These rules define flow permissions into and out of a VM. To link different Neutron networks together, virtual routers are launched and managed by the L3 agent. Virtual routers provide a routed path between project networks. Virtual routers can have a gateway set to an external provider network. This link provides a path for access to external networks. The IP allocated to the virtual router's external interface is used for SourceNet. SourceNet allows traffic to flow from internal project networks to external networks by translating source private IPs to the virtual router's externally facing interface IP. If direct access is needed from external networks to internal VMs, floating IPs are assigned to individual VMs. Access this way is accomplished through one-to-one NAT at the virtual router. I hope this video was helpful on the basics of OpenStack networking. Thanks for watching, and if you can, say hello on LinkedIn.